Well, I hope everybody had a great spring break, were safe, and all of that. And if you went somewhere, you had fun. It's amazing. I had one of the scouts in my scout troop. His family went to Germany and they got stranded because of mechanical problems. I heard of another high schooler, junior high. She went with her family to Hawaii. All I did over spring break travel wise was I went up to Haynesville there in North Claiborne Parish and pulled some cables and did an installation. So, anyway, if you went somewhere, great. If not, I hope you had fun otherwise, got some rest, maybe caught up on some things. And as we're finishing here, sections 4.7 through 4.9 on cues, I want to again say what a wonderful job all of y'all did on the first test. And I'll get you some homework out here on 4.7 later in the week. I mean, on chapter 4. But keep up the good work and hopefully you're learning some things. But as we get here into 4.7, we start talking about cueing theory, and it's um, different from linear programming. If you've done any linear algebra, let's say queuing doesn't try and find the optimal solution, but you might do things in queuing theory with linear algebra, probability, statistics, quantitative management, applied management science, operations, research. I actually, in working on part of this lecture here in 4.8, I actually went and found, still had some of my old textbooks and applied management, or one here on operations management. As I say, these I had back when I was a student back in the early 80s on that. So a lot of this stuff we're going to talk about in the especially 4.8 goes to quantitative analysis, quantitative management. So whether it's actually programming cues like we're talking about here with linked list or double linked list or otherwise, um, you see cues in a lot of so many areas, and we'll talk more about that as we work our way through this section. But we talked about cue, remember, as a first in, last out area, LIFO, where you're taking things from the rear, you're putting into the rear of the queue and you're extracting from the front, and every node had a link to the node behind it. And so that was fine. You kept track of the rear and you kept track of the address of the front. All, but we're really getting a little bit here into 4.7, into doubly linked list. And as I say here, the book has some things in here for NQ or DQ type of operations. We'll talk about that in a couple of minutes. But it's very enlightening to me to see how that Java handles those things. I remember certainly when my first exposure to linked list was back in 1981, 82 in a data structures course over at Tech using the language, as I said, PL1, programming language 1. We had to handle keeping track of those pointers and all that as a part of each of those nodes. So you have that here. It's already built in. We'll get to that. Book talks a little bit here about something known as a priority queue, where that you're able to remove from any point of the queue based on priority, but that's chapter 9, so that's there in 346. But you've got to remember, and it doesn't matter how you're programming it or what, you've got to allow for data exceptions. Whether it's an empty queue, a full queue, attempts to add the wrong type of element. Uh, Sometimes you might have the program notify the user if an operation failed to change the queue. And so it talks a little bit about NQ, ENQUE, UE, which returns true or false if the item is added to the rear. DQ, DEQUE, UE returns null if empty, otherwise removes the front element. And you got to think about, well, if your queue is handled in an array as such. What happens if you attempt to add to a full or a bounded queue or add a duplicate? That's certainly a possibility. Or add an element that doesn't fit some criteria if the queue is empty. But as I say, I think as you're working your way through programming, you've got to continue to learn about the possibilities. What could be the possible problems? And as I say, the more experience you get, the better and more encompassing your programs will be. And so we've talked about using operations that have been tested and proved to be working, and then adding new features over time. And so as we're getting here into around 250, somewhere like in that end, 251, we get to the glass queue. And with the glass queue, it peaks at the very front or the very rear element type of deal on it. And so you can go through it. Say here it's on 249 where you can peek at the very front or the very rear element where you can add or remove. Plus, not just add or remove, but look and see what's at the very front or the very rear. And so they've got this code here, glass queue interface. And the second line of code, public interface glass queue interface sub T, and that extends that queue interface down a level. So you're starting to see this a little bit on this public interface. So it's just saying, hey, you got to allow methods for abstract methods in both interfaces. As I say, this is where it takes one interface and implements another. And so you have this GlassLink Q Java over a page or so, talking a little bit about interfaces where you have that public class link glass queue, which it says extends the linked queue and implements the glass queue interface. So I'd say all it's doing here on this code on 250 is implementing where you can peek it, but it has a thing is empty, returns null, otherwise return the front. So it brings the front element of the queue out for you to use somewhere, but it doesn't change the pointer, it doesn't delete it. So you gotta think about that, but we'll talk about glass queues a little bit later on. Let's say it assumes you've got a statement if is empty, right there, middle of 250. Then it's saying, hey, if this queue isn't empty, it returns the null, otherwise it returns the front value. So, or the rear end of it. So you have that, and then they get into double-ended queues where they say, okay, well, if it's a stack, you can only look at the top. But if it's a double-ended queue, then you can add or remove from either end, just as a regular queue you put in from the back and everything gets pushed out through the front. So you can have this double-ended where you can do operations at either end, and it's called a deque, D-E-Q-U-E, pronounced deque. And so there's some code on that on 251 and all that. And so it just kind of says, hey, we can add to the front, we can add to the end. And there's a thing there also of keeping track with some linkage. But, just kind of be aware of that. But to me, kind of the main part here of 4.7 is the idea of doubly linked queues. So each element points to the element, each node points to the node in front of it and the node behind it. So that is really a way as you implement a double-ended queue where that you can add to the front, delete from the front, add to the back, delete from the back, things like that. So the main thing you have to do is you have to take that node and you add a second pointer there on the front end of it that points to the node ahead of it. And so by adding that second link, then you can get to the node in front either way. And so let's say there are three different variables in each node it talks about there on the top of 253. You have the actual information. You have a variable which they call link, which is a link to the node following it, to the rear of it. And then you have a link called back, which would take you back towards the front. And so that's a link to the node in front. And so you have there where all nodes there on the top of 253 point to the node ahead of them, and but for except and all the nodes except the first and the last have two links. The front and the last node have nulls for the pointer forward or the pointer backward. Now, this code here for this DLL node on 253, notice it is not in the CH04 subdirectory. It's in the support folder or subdirectory off the main book files folder that you downloaded the programs into initially. So as I say, it just sets up the node with the locations for the info, the front and back pointers, things like that. And so it adds some forward and back links. And I went through here and you see you've got the code there for it. And I made a note there like after that private T info, right before the private DLL nodes of T, forward and back. That's where it's actually creating the nodes with the information and the forward and back pointers, things like that. And you can have things like circular linked list where the rear node points to the forward nodes. And you can look at things eventually of removing the nodes from the rear, as long as your list is not empty. And so it talks a little bit here about on 254 about to remove D. You get that element D, then you get the address there on the forward point because D is at the end. So remember the rear pointer pointing to the next element is a null. So then you get the address there from node D of C, which is ahead of it, that pointer. Then you set the rear pointer to that address, and then you go to the address of C, and what did have an address of D, which no longer exists, you change that pointer there in C to null, and then you decrement your number of elements, and eventually that area memory that held D, it gets taken care of by the garbage collectors. And so we'll talk a little bit more about Java collections, added many of these functions. It's got the DQ interface, which could be used for a stack. It's talking about their different library classes, array DQ, concurrent link DQ, link blocking DQ, and linked list. And so we'll talk some more about some of those. But you've got some code here on page 256 there that just repeats the strings. I will print out strings of characters as you enter them. And we've already kind of looked at the DQ strings, using it as an array, and outputs the strings as in order. So not a whole lot new with that code right there, although it does handle removal and all that. So section 4.8, I really got into. As I say, some of my background having an MBA, quantitative management, system simulation. As I used to teach a course on system simulation, all of those things. And so it starts talking a little bit about figuring out how long people stand in line. And that is something that certainly is a concern of management and otherwise. And queues are everywhere. Lines are everywhere. Traffic types. I mean, last week I had to go up to Plain Dealing, and if you live there in North Bossier, you know where that they're adding to the turn lanes there at Benton Road and I-220. Well, it took me 45 minutes to go from about less than a mile, 2 miles there, headed north at 220. So you're used to queues for everything else. You're looking at computers. It talks a little bit about print queues, process queues, all of those type of deals. As I say, you've got to look at, as you get into queuing management, quantitative analysis, operations management, are whole areas of this. And you have to look at, well, how many people are in line on average? What's the cost to the business of additional servers, clerks, machines, printers, versus the cost of lost sales or waiting time? And so you certainly, as you get into management, if you go into quantitative analysis, or maybe even you look a little bit, we'll talk a little bit about gaming in a minute. There are various terms. There's a term balk, B-A-L-K. Now, if any of y'all are baseball players or baseball fans, balk, it's where that there really isn't a pitch or whatever, but it looks like there could be. Well, in quantitative analysis, operation research, queuing theory, balk means you as a customer leave the store. You put your stuff down. In a grocery store, you got to think, well, what if somebody gets mad at how long the checkout line is and they leave that $15 T-bone steak just in the aisle or wherever? Well, the store just lost $15 or more on that steak that they got to throw away. So, you've got to look at that. I saw people there on Benton Road balking. They said, well, this line waiting to go north is too long. So what did they do? They made a U-turn and headed south on Benton Road. And I don't know whether they were going to try and go up another way or go over to Airline or something. But you see people who turn around in traffic. And so how to handle queues and lines is very important. And Disney came up with, rather than having you stand in this long 300-foot line, waiting to get on a ride, Disney World, Disneyland, whatever, they came up with the idea of the wraparound queue. So you have the line that zigzags back and forth type of deal till you finally get where you're going. Well, psychologically, if you add that 300-foot long line down the sidewalk, well, you'd think, well, this is impossible. I'm not going to get on this. I'm not going to ever get there. But if you compact that 300 feet of waiting into 560 foots or 650 foot, your same amount of time, footage is the same, but you're going back and forth in that zigzag fashion. And you think it goes by a lot faster. You got people to talk to and all of that. Before you know it, you're at your destination. Disney applied management science to queuing theory. He just engineered the illusion of faster service. But as you're looking at queues, say, you got to look at problem formulation. What are your objectives and criteria? Data collection. Okay, you're going to simulate here this waiting time, and we'll get to that here in this problem here in 4.8. Well, do we use actual data? Where does that data come from? What type of distributions? Maybe you're familiar with random numbers. That's what's used here in 4.8. Maybe you've heard of binomial distributions, the Poisson distribution, exponentiation, all of those things. So if you're really going to be implementing a queue to use it to simulate a process with, you've got to have enough real world data from maybe observation, questionnaires, whatever. And then as you look at that data and simulating, well, then I say one of the first things you've got to do is look at where your distribution of your simulated data is going to come from. And of course, remember, you can always simulate in a few minutes of computer time what would take years of real time. So the confidence in the validity of your simulation model is critical to the successful use of it. So just kind of be aware of those things. As I say, and when I was going back, as I say, going through these old textbooks over here, still had them, you know. One of the chapters in it mentioned the trade-off of being served. Do you make a few people very mad at the service time and a lot of people just slightly mad, or do you really try and mess things up and you try to keep everybody happy and you wind up making everybody mad? So you've got to know 4 different things, really. The arrival time. Between how often does somebody arrive to do it? The second thing are the turnaround times. And it's got a waiting component and a service time. So once somebody arrives, then you know you start the waiting time. So then how long do they wait in the line before they're served? And then how long are they served? How long does it take to service them? And then once you can add the arrival time, and that's based from the beginning, we'll look at an example here in the book in a second, on that, then we add to that the waiting time and the service time. Adding those 3 items gives us our finish time. So the book goes through here and they show some code on service times, this customer class, over on page 260. But one good thing they've done here, and this is under the book files in the support package. So you have here this support off the main, but notice here on the code on the top of 260, it states very clearly what the preconditions are and it's the post conditions. And also these simulations assume that a customer will pick the shortest appearance. So everybody's coming down the same queue, and then they can go to the different arrival times. Different queues, and they can't jump from queue type of deal. So you've got here on 260 this support package. It has return arrival time, return service time type of deal. So it starts running here on 261. And so they say, okay, well, we're going to look at how this simulates. So the first arrival comes 5 time units after, and this is kind of what's graphically shown over here back a little bit on 258, 259, but actually when you get into how it's generating, because you're going to give it as a part of this the different times. So it says, okay, the first customer arrives at interval 5. So that's 5 clock whatevers from the start. Then the next person arrives at number 7. So they come in at 7. Well, it takes the first person 5 to be served. So 7 comes in, they enter the queue, and so they start at 12 because they had to wait for that additional time for the person to be finished. Then a third person arrives 4 after the 7 for number 2. So then they get started, they finish up when they arrive at 16. And then the next person arrives 10 after. So it's there 26 and all that. So you go through and it looks at using here some code here on this customer generator.java here on the bottom of 261. And so it generates with random numbers. As I say, we got to look on random numbers. Remember, random numbers are important and used a lot. But random numbers at times are not maybe completely random. Some computers use the same order of random numbers every time you run a random number generator. So sometimes you even have to seed the random number generator with a random number or maximum value, things like that, for what you want it to do, where you don't wind up with the same conclusions multiple times. So this code here is just going through, it's generating random arrivals of people and things like that. And then we get into the simulation. As I say, it allows you, we're here with this program, to run at different times with different numbers of queues, different number of customers. It'll put the customer in the queue with the smallest number of elements. And it also uses that glass queue to peek at when an element or customer is finished. So it kind of knows how long randomly each customer is going to take. So as it's bringing elements in with new customers, then it's removing them or it's adding them each time. And so this simulation program here on top of 262, all that, it is in the simulation subdirectory folder. Actually, it's 264. So you got to go up to book files, and under book files, and you see simulation. And so then you can, sorry, it's in the CH04 folder. Sorry about that. So it's the simulation subdirectory in the CH04 subfolder. Because several of the files in this chapter aren't in the CH04. Some of them, as I say, are in other ones. So it uses this random numbers, comes up with an average wait time, and uses the glass queue for queuing things up. And as I say, with all of these, you need to run it a little bit, see what it does. But this simulation program looks at max time and works its way through. And there are actually a couple of versions of it. There's one of them that goes through and handles it as a command line interface. And it talks about that on 267, where it has two versions of it in the CH04 apps. It has the application of it, which is command line, and then it has a graphical user interface. Talks a little bit here at the end of the section about, well, if you do the command line, you at least can see from run to run where you're giving it different interval times, and then with the number of queues type of deal and number of customers, the average waiting time, and whatever. And notice here on 267 when they ran it, where if they had 2,000 customers and they only had 2 queues available and same inter-arrival, service time, all that, if average wait time was 1,185, whatever time units we're using, they upped the number of queues by 1 to 3, and notice the inter-arrival time, waiting time, reduced to 5.74. So 72. So it's showing here in this simulation program, how adding one more queue, one more server type of deal, then the efficiency of it. So look at those things, and as I say, run the program, go through, test it, and that's really everything out of 4.8. So 4.9, you get into concurrency, interference, and synchronization. And I like this section. brings out some good points. Because certainly as y'all get further along, particularly some of y'all who are interested in gaming, then the multitasking, multiprocessing, all of that is going to become more important, where you have concurrent programs that consist of several interacting sequences executing simultaneously. And it goes back to the old idea of time sharing, where that your CPU gives each program running X amount of clock ticks and then moves to the next and moves to the next and moves to the next and all of that in more of a round robin situation. Um, so if it's a single processor or maybe multiple processors type of deal, multiple processors, you can have different parts of the program all running at the same time. So it's done in real time. But it talks a little bit about producers and consumers using the queue. Producers create tasks and put them in the queue. Consumers remove a task from the queue and execute it. And it's very possible that maybe you'll get more into this queuing theory of concurrency, interference, synchronization. If you take the operating systems class, or maybe the other half of this course on algorithms or database or compiler construction, all of those upper 3 and 400 level courses, you'll be more and more exposed to these ideas here in 4.9. So you got to look at terminology. You got to look at some code here. You'll look at on executing concurrently. It's got some real good examples here in 4.9 of where the code sequences can interfere with each other. It has a couple of different sequences that are going through and adding to a counter. And in some cases, because of when they act and when they don't act, as to whether the counter gets incremented correctly or not. Um, so they talks a little bit about synchronizing execution so that interference doesn't happen. And so, as I say, there's this CHO4 concurrency folder. And but they talk about each program a little bit here with threading, where each program has a main thread, and then the main thread can generate additional threads all running concurrently. And the program ends when all the threads end. And these ideas of threads actually are built into the Java specifications, language package, things like that. So there on 274, they talk about this command called join. And join, you provide it with a parameter and says basically that the main thread should wait until thread T finishes before continuing. And so then we get a little bit into interference there, and you see there where it's talking there on 274, about 5-6 lines down, underlined T dot join parentheses, which is saying, okay, main thread, wait till this thread T finishes before continuing. But then we get into interference where two or more processes or threads attempt to make changes at the same time to the same variable. And I say that's where you can get unintended results. Maybe you've looked at a database. I love in the 115 when I talk about databases and record locking. Say, okay, if you're fan, I've got, let's say this semester I've got a student who is from Central America. And so he flew back to where he was from there over spring break. Actually carried one of the other soccer players with him who's from Germany. And so we said, okay, well, if you're trying to get a seat there for the two of you flying south and you want 14E, well, while you've got that diagram of the plane pulled up, you want 4 seats, 14D and E for each of y'all. And if when you're out there on that plane, you're going to make sure when you're making your reservations, you got that diagram of the plane up that nobody else can get in 14E. So as I say, you've got to think about record locking as such, or locking of variables where each thread can only make changes to it accordingly. And I'd say it's got here all of these ideas under synchronization with these programs here of a synchronized queue, synchronized counter, and all of those are under the Chapter 4 concurrency folder. So, as you look at whether it's the program on 276, 278, all of those things, as I say, 276 runs this program on sync counter that says, okay, if one thread is incrementing, then no other will be able to um, remove from it. This Demo 05 program, it talks a little bit about different versions of it and letting it run there with the expected value of 10,000. It gets here into 278, this Demo 06, where it's going through and just adding to a counter with two different queues. Puts the numbers 1 to 100 in a queue. You got two threads that remove from the queue. And the author talks about, well, they ran this program 10 times and got the correct results of 5,050. The 11th time they ran it and they got 4980. The 16th time they got a null pointer, etc. and exception, excuse me. So the threads were interfering with each other. So as I say, it's here, it's under that concurrency subdirectory. And so just kind of be aware of it there on 278 under the threads. It imports the queues type of deal. And so imports in threads and queues. And as I say, goes through and counts, but they add to it a little bit of code here where that, and we'll talk about that in just a minute, called synchronized. So by adding the word synchronized to the code, then it returns the correct information. So you look over a couple of pages later here on 280, and where they have their operations are synchronized for concurrent access. And so you have one that creates the queue, one that removes things. And so you see where it says our rear side, but look there at, and I've got it here on the notes in the bottom of the page, my page 37, public synchronized void enqueue type of deal. And you actually see that there on the definitions of there, the 2/3 of the way down on 280. And then you have there over at the very top of 281, public synchronized T DQ. So you see there with the word synchronized added to the code, then it keeps things organized for you that way. So just kind of notice where it's adding some things. I say those are top of 280, bottom of 280, top of 281. Then you have where it's synchronizing those operations. You've got another one where they look at if it's full. Several places down there, 281 goes through that. And so that's by using that synchronize command throughout, then it waits for each one to finish type of deal. And you can read the code there. And then each thread waits on the other by putting that reserved word synchronized in there. Then it sets it up and waits for each thing to wait. And then the last thing it talks about here is this collections class, and I think we're going to talk more about collections later on. And so, yes, chapter 5. And it talks about how there are 9 different classes in the library to implement the Q interface. And it talks about, well, things with standards and implementing these collections, good, bad. It ends up talking here in the chapter about hashing. And I don't know how much y'all have done with hashing techniques, things like that. But hashing techniques are various ways to easily find records out in a database or a file of some sort, figuring out where a given record is and getting to it. It goes somewhat back to our idea of the binary search, binary sorting type deal of dividing and conquer. So there's some things here, and as you get further along, you'll learn more about hashing techniques, things like that. So just a little bit there at the very end there on 283 about those. And that's really everything here on 4.9. So as I say, y'all keep doing what you're doing. I'll get you some assignments out as such here in chapter 4. And we will get into collections, which will be our next topic. So have a great week. Call me if you need me. Email me. My C#@shreve.net is back up and running. I had a very interesting thing from them. I'll probably forward that email. And from the company, basically what happened on the email was they're using one data center, and that data center contract or whatever ended, and they had to try and start moving things much sooner than they figured. And it was an interesting week and a half, 2 weeks, but everything is back to normal. Everything's forwarding and all that. So have a great week. Be careful, and we'll talk to you soon.